Alright, so hopefully this will be the last one of these you guys have to see. I did just get back from the doctor today. Apparently I got some type of viral infection, so I'm finally getting some medicine for that, help with the nausea and whatnot. I should be back in class on Friday, but yeah, so anyways, these notes today are going to be covering the topics of imperial versus molecular formulas and percent composition by mass. This is new material, but it is directly tied to molar mass, and it's just another application of molar mass. So it's not going to be your simple dimensional analysis, two-step, one-step problems anymore, but a completely different type of application from where we're with molar mass. So basically just a quick review of some stuff we've already done. You guys should be familiar with what a mole is, and of course how that is expressed with Avogadro's number. So a mole in Avogadro's number, a mole is just a way to count a group of atoms. Since atoms are so small, we need a way to quantize them to make it a bit easier to deal with. Another big important concept we've been dealing with is the idea of molar mass, the mass of any 1 mole of any element. So if you have a mole of hydrogen atoms, you have a mass of 1.01 grams. If you have a mole of carbon atoms, you have a mass of 12.01 grams. So those masses is going to be the mass of that 6.02 times 10 to the 23rd atoms. So you get 6.02 times 10 to the 23rd particles per mole in Avogadro's number there. So molar mass is actually going to be very important for what we're dealing with today as far as math goes. So the math isn't that complicated, just some percentages with molar mass, that's all it is. It's just going to seem like it when we start, but that's just the definitions. So what you guys have been doing mathematically so far is mole conversions using dimensional analysis. So you guys have been using dimensional analysis and mole conversions to convert either a 1-step or 2-step problem, where you're converting from like grams to moles, or if you got atoms all the way to grams. So grams to mole, that is going to take 1 step, but atoms to grams will take 2 steps. First you'd have to convert atoms to moles, and then moles to grams. So you have that whole flowchart thing we worked on. So anyways, that's the kind of math that you guys have been doing. Today we're going to get into a new application, there's what I'm looking for, a new application of molar mass. What else can we use molar mass to do? And how useful is this tool? So to do that though, there are 3 definitions we have to get into. We have to define what empirical molecular formulas are, and we also have to define percent composition. So we have to define 3 things. So the first thing is going to be your empirical formulas. This is where we're going to start taking the chemical formulas that we've been writing and really starting to relay them back down to like, how does this actually apply? How do we know that these are the chemical formulas that we're dealing with? So I got empirical formulas, and an empirical formula is going to be the smallest whole number ratio of elements in a chemical formula. So the empirical formulas are the simplest formulas. A couple examples of those kind of give you an idea of what I mean. If we have any ionic formula, so remember you had to reduce all of your ionic formulas to their simplest form. That means any ionic formula like NaCl that is an empirical formula. The ratio here is 1 to 1. It's already in its simplest form. Or you could have something like magnesium chloride, NgCl2, where you have a ratio of 1 to 2, simplest whole numbers. Even something a little bit more complicated, Al2, aluminum carbonate, CO3, 3. Even though you have some numbers right here, you got a 2 and a 3, well, that's still the simplest whole number ratio. So this idea of simplest whole number ratio is something we've been applying to ionic compounds for a very long time. Now, covalent compounds do not always follow this rule, so you only get some covalent compounds here as examples. So some covalent compounds, for example, water, H2O, something like sulfur trioxide, SO3. H2O is a 2 to 1 ratio, SO3 is a 1 to 3 ratio, simple as it can be. You can have methane, CH4, but if you take something like C2H8, and you're like, that's an empirical formula, it's not. Because 2 and 8 are both divisible by 2, so C2H8 is not an empirical formula. The ratio there is not as simple as it can be. This chemical can exist, and it can be a molecule, but it is not an empirical formula. It is not in its simplest form. The simplest form of this formula would be CH4, which of course I already have written right there. Because the 2 is divisible by 2, making 1, 8 is divisible by 2, making 4. So even though this chemical exists, it is not an empirical formula. So anyways, that's just a definition thing. The reason we have to define empirical molecular formulas differently is because of how percent composition works out. But we'll get to that in a minute. So the definition for empirical formula is the smallest whole number ratio of elements in a chemical formula. Now a molecular formula, a little bit different. And a lot of people get a little bit confused about these definitions. It's just how it is, I guess. But see, a molecular formula specifies the actual number of atoms of each element in one molecule of a substance. So molecular formulas are going to be what the substance actually is. For example, this C2H8 is a molecular compound that has the empirical formula CH4, but the molecular formula C2H8. However, water, H2O, that is what the molecule actually looks like. Therefore, this is a molecular formula for water. It is also the empirical formula for water because it's the simplest form. So the definitions, molecular formulas, can also be empirical, but not all empirical formulas will be molecular. Molecular formulas are what the molecules are actually made out of, and you're going to see these with covalent compounds. So some other examples, you could have something like S2O6, that could exist. 2 and 6 is not the simplest form, so it would be a molecular formula. The empirical formula of this guy, the simplest form of S2O6, would be SO3. So, another thing to point out, just to remind you guys of that we've been talking about, these subscripts, we talk about how many atoms, right? So for every one molecule here of C2H8, I have 2 atoms of carbon and 8 atoms of hydrogen, I could also express that as for every 1 mole of C2H8, I have 2 moles of carbon and 8 moles of hydrogen, if you recall that from Monday. So I could either be looking at an individual molecule, which will be really hard to do because molecules are tiny, or I could focus on a mole of them, which is much easier to do in actual experiments. So usually you're going to see this mole ratio come about. So these subscripts are often referred to as mole ratios. So your mole ratios are going to be these subscripts in chemical formulas. They describe the relationship of how many carbons and how many hydrogens do you have in this compound. So that's an older vocabulary word, but just want to kind of bring that back up because it's important when we were talking about how these formulas are related to the idea of moles. So, how do we determine the molecular formula versus the empirical formula? And that's another idea down here, just kind of want to make a note of real quick. So chemists, just for your notes, determine the molecular formula based on its measured molar mass and its percent composition. And percent composition here is also this third word down here. So we got empirical molecular formulas and percent composition. So what is percent composition? So let's slide this page up a bit. Move some stuff around. So today is mostly just notes. And I realize I'm writing all proper and stuff, but I really don't have to. Could use some of this margin space, but I can't get into that yet. So, percent composition by mass. Get you guys a working definition here. What is percent composition by mass? Percent composition by mass is going to identify the ratio of atoms in a compound. Another way to phrase that is this is going to allow us to identify the mole ratio. So we're going to be able to calculate mole ratios using percent compositions. Now, percent composition is more of a mathematical tool, so a word definition doesn't help too much in my personal opinion. So you have that if you want it. Another way to write this, of course, we have to make a little assumption here for this way of writing the formula. We have to always assume 1 mole of a compound to make this formula work all the time. So if we assume 1 mole of a compound, then the formula for percent mass, by the way, this is what percent composition by mass. Oops. Forgot the A there. Percent composition by mass, I always write it percent mass with a percent symbol and mass right there. So when I write percent mass, that is referring to percent composition by mass. Just a little bit of shorthand, makes life a lot easier when doing these problems, going to be equal to the mass of 1 mole of a specific element, so an element, so divided by the mass of 1 mole of a specific compound. And to make this into a percentage, you multiply that by 100. If you recall, we talked about percentages very early on in the year. I told you every time we deal with percentages, because we're going to do that a lot, you get a general formula where percent is going to be equal to part divided by whole times 100. And that's true every single time. The part of a formula is an element, and the whole part, like the whole thing, is the compound itself. For example, if you wanted to do percent mass of water, right, just for example, percent mass of H2O, you would be calculating the percentage of hydrogen, which would equal the mass of hydrogen divided by the mass of water times 100. And the mass of oxygen, which would be the mass of oxygen divided by the mass of water. And we can actually do this calculation real quick, because the mass of hydrogen on the periodic table is basically 1 gram. The mass of oxygen on the periodic table is basically 16 grams. So the molar mass of water will be about 18 grams per mole. 1 plus 1 plus 16. So if you actually want to figure this out, what is the percent of hydrogen in water? Well, 1 divided by 18 times 100 would be about 5.56% hydrogen. And water would also be about 16 divided by 18 times 100, about 88.89%. Oh, shoot. I just did something wrong because I'm not feeling well, of course. My number here is wrong, right? That is not correct. The reason that's not correct is I put 1 gram right here. How many hydrogens are in water? 2. There are 2 hydrogens in water. What is the mass of 2 hydrogens? 2 grams. Each hydrogen, so the hydrogen in water, you have 2 of them, so you have to have 2 grams there. That's my bad. 2 divided by 18 times 100. That makes it a little bit better, 11.11%. If you notice, if you ever add your percentages together, you should get about 100%. So 11.11 plus 88.89, that'll give you 100%. Your percent composition should always add up to 100. But anyways, your answer for this example, mass percent of H2O, 11.11% hydrogen, 88.89% oxygen. Now, we're going to be working another example. That's just a quick throw it out there kind of deal. What is percent composition by mass? So, I'm trying to think how I want to break this down. To conserve some paper, I'm just simply going to slide this one up one more time. And we're going to work a couple examples. So you got your 3 definitions, and now we're going to see how to do some math. So how to actually work through this stuff. So yeah, this video is coming out to be a little bit longer than the other one, but that's fine. We had 3 definitions to worry about too. So, still. So the first thing we're going to be dealing with, the first type of problem, will be a percent composition problem. The way you'll see these written will be something like this. Determine the percent composition of something random like baking soda. Now, you guys don't know what baking soda is, so I'd have to give you the formula. NHCO3 is the formula for baking soda. Now, I could have just given you some random formula and not told you a name. The name doesn't really matter, but usually you're going to see chemical names tossed in here as well. So how do you solve it? Well, the first thing you have to do to solve this problem is find the molar mass of NaHCO3. So you got to find the molar mass of this guy. Now you need the molar mass because you're going to use the molar mass in your percent composition. So to find the molar mass, of course, you have the mass of sodium, which is roughly 23 grams per mole. You have the mass of hydrogen. Well, I'm getting ahead of myself. We only have one sodium, so we're going to take 23 grams and add it to the mass of one hydrogen, 1 gram, plus the mass of carbon, 12 grams, and the mass of oxygen we have here, we got 3 of them, so 3 times basically 16 grams. If you don't recall, 23, 1, 12, and 16, all of those numbers from molar mass come off of the periodic table. So look up the element on the periodic table and use those molar masses. Typically, I would suggest keeping 2 decimal places, but I've rounded these to make this a little bit easier on us all. So, if you do all this math, 23 plus 1 plus 12 plus 16 times 3, you should get about 84 grams per mole for the molar mass of NaHCO3. And I'm just going to double check that because I've already made one mistake. I don't want to make another one. 23 plus 1 plus 12 plus 3 times 16. 84, perfect. So I did something right there. All right, now how do you use this information? So the second thing you're going to do is take all of your different atoms, and we're going to have to calculate a percentage for each individual one of them. So I'm making myself about 2 lines here so I can keep this nice and neat. So if your notes this first time, I would suggest, keeping it nice and neat. So do what you need to do. But I'm going to start this next one down here on this other page. All right. So to solve this problem, we're going to be looking at the percentage of all of these atoms. We're going to start with sodium, just because it comes first. It's kind of arbitrary. So the percent of sodium in baking soda is going to be the mass of sodium. Remember, we assume 1 mole. So 1 mole of sodium has the mass of 23 grams. And we assume 1 mole of our compound, which has a mass of 84 grams. We're going to multiply that by 100. So 23 divided by 84 times 100 should give you 27.38% sodium. And for hydrogen, we're going to do the exact same thing. The mass of hydrogen, we only have 1 of them, so the mass of hydrogen here is 1 gram. The mass of my compound is 84 grams. So we assume 1 mole of everything times 100. If you type that into your calculator, you should get 1.19% hydrogen. Percentage of carbon, the mass of 1 mole of carbon is 12 grams. The mass of 1 mole of sodium bicarbonate, baking soda, is 84 grams times 100. 12 divided by 84, 14.29% carbon. And then finally, you get to do your oxygen. Oxygen is where it gets a little bit weird. See, oxygen, you have 3 of them in this compound. So you have to take that into account when you figure out how much mass of oxygen is in this compound. 3 multiplied by 16 grams divided by the mass of the whole thing, 84 grams. times 100 to make it a percentage. Now, when you type this into your calculator, there's really, several ways to do it. You can type this in as one big problem if you like. Typically, what I would do, I would just take 3 times 16, hit enter, and then hit the division button just because that's how I've always done it. You could type it in all together if you want, but I never actually type in the times 100. I just move the decimal 2 places. Still. So you have to have the 3 times 16, which would be 48, and you're dividing that by 84, multiplying by 100. So you get the oxygen is 57.14. Around that, 57.14% oxygen. Now, if you take all these percentages and add them up, you should get basically 100%. 27.38, 1.19, 14.29, and 57.14. Oopsies. And we get exactly 100%. So your percent composition by mass should always tally out to be 100%. Now here's something you guys are not going to like to hear. You are not going to calculate percent composition by mass very often in real life because there are machines that do it for us. Usually, if you obtain some type of random sample from a crime scene or something, you're going to obtain data that tells you this is the percent composition. And then it's going to be your responsibility to figure out what the formula is. So you're going to be using percent composition information to figure things out. So how do you do that? Well, that's where the whole empirical versus molecular formula thing comes in. So that's where this second type of problem is going to come in. Really, there's only 2 types of problems. There's just a little bit of extra information to tack on to the end of this one. So I'm going to get that percentage thing out of here because we don't need it. Everything else should fit on this page, but I got some extras if I need it. So the second type of problem is going to be more like what we're going to be faced with in real life situations. What if you know what percentage? How can you calculate the formula? Life's a little bit more difficult this way, but not by too much. So same thing, you're just using molar mass to do some calculations. The way you would see these problems phrased is determine the empirical formula of a compound sorry, the nausea is still around, that has the following percent composition. Oopsies, 2 N's. 40% carbon, 6.67% hydrogen, and 53.33% oxygen. Now, I would even go ahead and tell you that this is a white powdery substance found, I don't know, somewhere. Doesn't matter. If you're dealing with a crime scene, you're going to have more information. Now, this specific compound is made up of carbon, hydrogen, and oxygen. And what you are trying to do is figure out the mole ratios. So, a couple easy little steps here to remember. The first thing is a simple assumption. Assume 100% of your sample will equal 100 grams. Because to figure out a mole ratio, you're going to have to use molar masses, which means these percentages are useless to you. You need grams. Well, if 100% is 100 grams, that percentage is a gram symbol, right? You guys notice that? 100% equals 100 grams, 1% equals a gram. Therefore, 40% equals 40 grams. So your first thing to do is assume 100% equals 100 grams. You don't have to do that. I mean, you could pick any sample size you want. Just anything other than 100 requires you to do more work. So pick 100 grams for your sample size. And that makes your math so much easier. The second step is to use, molar masses to calculate your mole ratios. And there's actually a third step, but you don't always have to do it. In this case, we're going to have to. You don't always have to. But we'll cross that bridge when we get to there. So the first thing you do, you set it up kind of like we did the percent composition one. We got 40% carbon. I need some space to do my work, so I'm going to give myself a couple lines. 6.67% is going to be hydrogen. And then 53.33% is going to be oxygen. Carbon, hydrogen, oxygen. Now, step one, assume a sample size of 100 grams, which means I have 40 grams of carbon, 6.67 grams of hydrogen, and 53.53 grams of oxygen. And now, to get a formula, I just need a mole ratio. So to get a mole ratio, I'm going to use the molar mass of each substance to convert it to moles. You guys remember we did that one-step calculation, grams to mole? And to do that one-step calculation, we had to divide by the molar mass. That's literally all you're doing right here, just 3 times. So the molar mass of carbon, you have to look up on the periodic table, is going to be 12 grams per mole. We're starting with grams, so that molar mass has to go on the bottom for every 1 mole. Feels like my Zofran's starting to wear off and I can't take another dose for another 5 hours. That's great. All right, so 40 grams of carbon times 1 over 12. Same thing as dividing by 12. So if you type into your calculators, 40 divided by 12. Well, I made it this far. Basically done. 3.33 moles of carbon. Do the same thing for hydrogen. The molar mass of hydrogen on the periodic table is about 1 gram for every 1 mole. So 6.67 divided by 1, 6.67 moles of hydrogen. And then, of course, you've got oxygen. The molar mass of oxygen is 16 grams for every 1 mole. So 53.53 divided by 16, 3.33 moles of oxygen. And now you have your mole ratio. So you could write your formula, C 3.33, H 6.67, O 3.33. If you did that, you would have the wrong answer. Because I would ask you, can you have fractions of an atom? No, you can't. You cannot have fractions of an atom. So we can't have decimal places here. We need this to be a whole number. So the third step is to make your mole ratio whole numbers by dividing by the smallest number of moles. And this is the really cool thing when you see how this works out. So I'm just going to rewrite this right here. 3.33 moles of carbon 6.67 moles of hydrogen and 3.33 moles of oxygen. The smallest number here is 3.33. So we're going to divide all three of these by that same value. Well, 3.33 divided by 3.33 is 1 mole of carbon. 6.67 is 2 moles of hydrogen and 1 mole of oxygen. So our formula is C1H2O1. And that is how you calculate your empirical formula. Not more work than percent by mass, but it requires a trick at the end, this third step. Now, the last kind of problem we're going to look at, and even though I say last kind of problem, it's not actually another problem. It's going to be the same problem, but I'll number it as well. This is for molecular formulas. And it would be something like this. What is the molecular formula of CH2O I've written this wrong. Is not supposed to be there. What molecular formula of CH2O would have the molar mass of 180 grams per mole? And this seems like it's going to be difficult. It does. But it's not. It's actually going to be the easiest thing we've done so far. And it's still just going to be talking about ratios. Everything we're doing is about ratios. It makes it fun. So, to solve this problem, all you've got to do is figure out, well, CH2O is the empirical formula. The molecular formula is just some multiple of the empirical formula. So the empirical formula has a molar mass equal to 1 carbon, 12 grams, plus 2 hydrogens, 2 grams, plus 1 oxygen, 16 grams. So the molecular formula, the empirical formula, CH2O, has the molar mass of 30 grams per mole. The molecular formula which is a multiple of the empirical formula, has a molar mass equal to 180 grams per mole. How many times larger is 180 than 30? To do this, it's really simple math. 180 grams, well, I really don't even need the units here, but why not? Divided by 30 grams per mole. How many times larger is 180 by 30? Just divide them. 180 divided by 30 tells you that this is 6. The molecular formula is going to be 6 times larger than the empirical formula. So all you got to do is take this mole ratio 1 to 1 and multiply it by 6. 1 times 6 is 6. 2 times 6 is 12. and 1 times 6 is 6. My molecular formula for this compound that we commonly call sugar is C6H12O6. The reason we have to define between molecular and empirical formulas is because a molecular formula can be a multiple of an empirical formula, but this and this will have the exact same percent composition. Percent composition does not account for multiple moles. Anyways, I've hit the 40-minute mark, which means this is basically your entire class period. I'm going to type this assignment up as well onto this Canvas page. Tomorrow, since you can't really do it today, I don't really expect you guys to, you guys are going to be working on some practice problems. And I've misplaced the piece of paper. So, no, I haven't. It's right here. So anyways, tomorrow you guys are going to be working on some practice problems. You're going to start, it's just 6 problems all together across 3 different page numbers. And I'll type these up as well. Page 344, page 346, and page 350. On 344, you are doing number 54 and 57. You're doing questions 58 and 61. And you're going to be doing questions number 65 and 66. So those 6 questions will be your practice. This is going to be Thursday's assignment. And I should, ideally, be back in class on Friday. I mean, I was hoping I'd be back in class on Monday this week, but see how well that worked out. Anyways, there you go. And hopefully I'll see you guys soon.